Hi, in this video, I'll be going through what are cosets. And so, cosets are very important and they'll play a fundamental role as we move forward in group theory. So, we define the left coset to be the group G capital N, where N is a subgroup. So, we take a subgroup first, and then we form the left coset of it by taking an element in G and multiplying it. So we are saying this is the left coset of N in G. A similar definition for the right coset of N. So basically you're taking all the elements in N and multiplying it with G, and then forming this this group set. And AB will just be the union of left cosets of B where A runs through A, or you can just say it is actually just the elements of AB where A and B lies in the respective capital A and capital B. And you can show that actually GHA equals to GHA. So the left cosets, you don't need to do the operation H first then G because of the associativity in your binary operation. But what we like to remember is that the left coset may not equal to the right coset, and if they equal, it doesn't imply that BA equals to AB, but they are equal as sets. So what you're saying is that an element here is some element here, and some element here is some element here, if this was true. So if G is a billion, then of course your left coset equals to your right coset. And for all elements A in G, A is an element of A H coset. And so you can think about it, for all H will obviously be an element of H. So that is in the 1 coset. So H is a coset of H itself. Here's an example for you to see. So you take the subgroup 0, 2 and you form the left cosets and right cosets. So the only left and right coset you can see is 0, 2 and 1, 3. Because with the addition, you can take 0, 2, then you take 0 plus 0 is 0, 0 plus 2 is 2, or now you take 1, 1 plus 0 is 1, 1 plus 2 is 3. Then you take 2, 2 plus 0 is 2, 2 plus 2 is 4, which is 0, and lastly you take 3 plus 0 is 3, and 3 plus 2 is 1. So that's why you only have 2 left cosets in the end. So not all cosets must be distinct. And what you can now show is that actually these cosets form a partition of G, meaning the union to be the whole of G and their intersection is trivial. And to do so, we first need to show that G equals to the union of all these left cosets. And that is quite simple because G equals to G times 1, which is an element of G is an element of G n. So the left coset of n with G. So if that's the case, then we just take all these G and we run through G as an element of capital G of all these left cosets, and we're done. Now we just need to show that distinct left cosets have empty intersection. And that means we take 2 left cosets and we show that they cannot be equal. Or you can say that if they have a non-empty intersection, then they must be equal. So we just first take X element of the intersection because it's non-empty, and we can write it as UN and VM. Then we can multiply N inverse to both sides and we get that U equals to VM N inverse. And we know that M and N are elements of capital N. So M and N inverse is an element of giant M. So we can use that now as a M1. So we know that for any element of UT in UN, it equals to some element in Vn. This proves that UN is a subset of Vn, and you can likewise do the reverse inclusion by multiplying with M inverse. And so this shows that the 2 cosets with non-empty intersection must be the same cosets. And we are done with proving that these left cosets form a partition, And with every partition, you can actually form an equivalence relation, which we will talk later on. So, if un equals to vn, if and only if u is an element of vn. And this means that if and only if u equals to vn for some n, or you can just say that v inverse times u is an element of n. So these are all equivalent statements. And so it doesn't matter which candidate you choose as a representative of the coset. And so what you want to say is that if two cosets are the same, it means that B inverse times A is an element of H. And what's important about this theory of cosets is that we have this thing known as the Lagrange theorem. And the Lagrange theorem really is a powerful theorem, and it states that if G is a finite group and you know H is a subgroup of G, then we know that the order of this subgroup must divide the order of G. And namely, the number of left cosets equals to G divided by H. So we let the order of H be n, and the left cosets of H equals to k. By what we said earlier, we can form a partition, and so this left coset, we know that G equals to the union of left cosets. And so it will be the number of left cosets is H, so it's H times it reduces to now showing that what we want to show is that every coset is actually equals to have the same size. And really, that's by the definition of left coset H, we can map it into GH, and this is a surjection. And so by the cancellation law, GH1 equals to GH2 implies H1 equals to H2. And this proves that H and GH have the same order. And so because you can be partitioned, so actually it's just K times GH, which equals to K times H. And you're done. So I hope the proof is straightforward. You can read it again and leave any comments in the comment section if you don't understand. So with this Lagrange theorem, now we can say that the order of an element divides the order of G as well. So every element order divides the order of the group. And in particular, x to the power of n equals to 1 for all x in G. If G is finite, of course. So because you can just take the order of x and form the subgroup which is cyclic, then by Lagrange theorem, it divides G. And then because it divides G, we now know that it's clear that the order of G must be a multiple of the order of x. And so x to the power of n must equal to 1. And if G is a group of prime order P, then G is a cyclic group. And because we know that the cyclic group order divides G, and since G is prime, it must mean that this order here P equals to P. And so it must have that the cyclic group order equals to the order of G, and hence G equals to the cyclic group itself. So this completes the proof. And what we want to now state is that you can apply the same idea on the right cosets, and we see that the number of right cosets equals to the order of G divided by the order of H as well. And this means that the number of right cosets and left cosets have some sort of equality between them. And so we can define the index of H in G to be the number of cosets of H in G with this notation. So the index is the number of cosets. And actually, if H is a subgroup of K, which is a subgroup of G, then G, the number of cosets of H in G is actually the number of cosets of K in G times the number of cosets of H in K. And really, if you read, I laid out the proof here for you to read, and I'll go through it step by step now. So the idea is that you have the cosets of K in G and the cosets of H in K. What you just want to show is that GIKI is the forms are the cosets of H in G. And so if G is an element of G, then G is an element of GIK. And so G equals to GIK for some K in K. And because this K must be an element of KJH for some J, it means that G must be an element of GIKJH. So you know that the union, G is in the union. And now you just want to show that they are disjoint. So you just take two cosets and we show that they are equal. So if they are equal, then you can show that the intersection is non-empty. This means that I equals to A. And if I equals to A, it also means that KJH equals to KBH. And this also means that J equals to B. And so you're done with proving that G is just the union of these cosets. And because G is just the union of these cosets, you can just take the number of cosets equals to whatever over here, because it's G, KH is the index, then you G of this GK, and so you'll be done. So that's all for this video. I hope you have enjoyed it. Feel free to like, share and subscribe, and I'll catch you in the next one.